So we talked about the fire season, length of the fires, and number of the areas burned with climate change and so on. Does that translate directly to increases in CO2 emissions from fires? Doesn't seem to be so. These are modeled historical simulations of global wildfire CO2 emissions going all the way back to 1850, well before the population was so high and the inhabitation in the vegetation or close to vegetation would have been much lower as well, especially in places like California, for example, which burns a lot every year and creates a lot of news. So looking at change in modeled fire emissions and fire CO2 emissions in petagram carbons per year, you can see that historical simulations with all forcings, so that is including volcanoes, solar activity, anthropogenic greenhouse gas emissions, and so on. The numbers are here. And the historic simulations with only land use change forcing are down here. So obviously all forcings have increased the emission over this period, but over this period since about the 1960s they are both below this baseline period. Okay. Historical simulations with population forcing only is up here. So just the increase in population and its impact on forest, there will be many assumptions in these models. I'm just showing these to say how all attribution exercises seem to say that there's been a drop in the CO2 emissions because of fires in the last several decades. And these are observations based on some global fire emission detection, which is down here, which is actually well below the model estimates. Okay, so you can read the caption here. So basically the main message you would want to take is that it's not so obvious that the fire emissions are contributing more. As we said before, there is always a natural experiment being made by El Nino and La Nina on fires. The dry, warm conditions and cool, wet conditions, seasonally dependent, as well as the asymmetric El Nino, La Nina type teleconnections give us, for example, El Nino has many more warm spots in both seasons compared to La Nina, which you would expect, because here the ocean is taking up much more energy because the upwelling and strong cool temperatures, strong cooling of temperatures in the ocean soaks up heat like a sponge into the ocean. So the global mean temperature is reduced by a little bit, whereas during an El Nino there is a mini global warming. All that stored up heat in the ocean is released temporarily during El Nino, so it can actually amplify global warming for the short period, 6 to 18 months, over which El Nino affects the global temperature and precipitation. So those have fire impacts and well-known fire spots as well, dust storms and droughts over Indonesia and Australia and parts of Nordeste Brazil and down here in Argentina and so on and so forth. So those can serve as some validation points or field experiments for feedbacks as well in terms of emissions, warming, uptakes, and so on. So impacts on fire activity obviously comes from human activities like agricultural waste burning, land use change that we mentioned, ignition and suppression activities. So there are many fires set, sometimes intentionally but sometimes unintentionally by human activities, and humans are obviously actively trying to suppress fires all the time, and the jury is sometimes out on whether this suppression actually makes the fires more intense, for example, by creating changes in the dry fuel in a managed situation versus a natural situation. The climate-related impacts include, of course, precipitation, relative humidity, temperatures, winds, vegetation species composition, and lightning igniter. So these are just repeating some of the points in terms of aerosol indirect effects on fires and because of fires. So there is wet deposition and dry deposition happening. This is immediately removing some amounts, whereas this can lead to long range transport. For example, the fire-related aerosols from California were detected all the way into Europe, for example. Okay, so aerosol deposition on ice surfaces, what will it do? As we know, that's going to reduce the albedo and increase the melt rates. There are also biogeochemical cycles affected. Smoke contains greenhouse gases, carbonaceous aerosols, hydrocarbons, NOx, so N2O, CO2, methane, which also includes ozone, non-methane hydrocarbons and NOx, and so on. So lots of feedbacks, and this is now global and annual average radiation forcing for various impacts of fire examined in this study, which used a couple of models. This was the community climate system model, which is a precursor to the community earth system model, and ECM is from Germany, or no, that must be from the UK. Look it up, please. Okay, so this is just showing radiative forcing from carbon monoxide, methane, nitrous oxide, ozone, aerosol direct and indirect effects, aerosol biogeochemical effects, and climate biogeochemical feedback effects for 1850 to 2000. So you have some positive feedbacks here. The carbon dioxide forcing is negative, because the baseline depends on where the baseline is. But when you look at 2100, the projections into the future, radiative forcings change, and this is the fire examined seem to reduce the total radiative forcing when you include the 21st century into the whole period. Why am I showing it? Basically to show that people are beginning to consider fire risks, including all the fire interactions with vegetation, biogeochemical cycles, aerosol, direct, indirect effects, and so on. But you can see that the uncertainties here can be quite high, especially indirect effects of aerosol, which we talked about in terms of the microphysics of clouds and so on. And even the direct effects have significant uncertainty. Carbon dioxide feedbacks just from fires related CO2 emissions also have basically massive uncertainty around the zero line. But the main message here is that the 1850 to 2000 period has net positive total effect of wildfire or fire radiative forcing, whereas the adding 21st century reduces it. So these are the things that have to be taken care of in terms of improving the feedbacks in the models, or understanding them better in any case. Aerosols and radiative forcing from wildfires obviously affect albedo. So you can see the wildfire smoke here. There is Hurricane Lane being identified in this satellite image as well. So you can see the scale here. You're going from sea salt, which is a natural aerosol picked up from the sea surface. Dust can be natural from the deserts, or can be exacerbated by human activities like land use change, fallow agricultural land, and so on, deforestation, and black carbon, which is an absorbing aerosol and can greatly increase absorption because of reduced albedo. There is a Sahara dust, which is very bright. There is a typhoon as well on the picture, and so on. So obviously aerosols and greenhouse gases together have great effect on greenhouse gas and climate as far as fires are concerned. Maybe a little bit late, but I just wanted to show the aerosol direct effect where you have scattering and absorption, which affects radiation budget. And fires produce plenty of it. So do the volcanic eruptions, for example. But fire is an annual thing, whereas volcanic eruptions are very episodic. Indirect effects of aerosols include cloud properties, cloud brightness, temperatures, and so on, cloud reflectivity, and properties of rainfall, droplet sizes, drizzle versus heavy rain. There are also impacts on hurricanes and so on and so forth. So this is the next podcast. Let's leave the forests of the fire story there. But again, these are feedbacks that are very relevant for contemporary climate and for climate projections.